So I'd like to turn it over to Michael Kohler with just a brief recap. So we heard from David, compute and data supremacy. We heard from Don, a role for understanding the world through experimentation and the role of big ideas. I think Michael also agrees with the role for big ideas and, presented his own characterization of the future focused on understanding, decision, and coordination among the decisions, and, for example, through markets. And I think everyone agrees on this session that there's nothing to AI. So that was surprising and interesting. And actually, I do agree with that point. And I want to poke one more hole into a current way that AI is portrayed. And I think I'd like to hear Michael's perspective on that. So AI has been portrayed as deep learning largely, right? And so first of all, when I think of deep learning, it's just another technique like linear models or, mixture models and so on and so forth that has been chosen and has been supported by a huge amount of resources. And second, deep learning has serious limitations themselves. And so I'm just a user of deep learning, if any. Michael has actually done some in-depth technical analysis of deep learning models, in particular over-parameterized deep learning models. And I would like to hear from you, Michael, your opinion about deep learning models, over-parameterized deep learning models, in particular, when what kind of conditions they need to really perform at the level that's been portrayed in the media, in terms of, say, amount of data that's needed or signal to noise ratio. Do these models ever break down, Michael?
Okay, let me start. I'm not sure whether I will actually answer your question. Let me first start by saying that I should make my. I really liked both talks, and I'm one who is working on the mathematical foundation of deep learning since several years already, and I have first to confess, I think we are at the beginning with this. So I think we have some results for the pattern recognition, but nothing on the decision making. So the decision making will be maybe in the future, but let me talk more about the pattern recognition. Instead of pattern recognition, you usually make it in regression. So you study these kind of estimates as regression estimates, and then you look what can you say about them. And there are several aspects on this. The first one thing, regression, that's a function estimation problem. So if you estimate a function with a special class of, say, neural networks, you have some kind of approximation problems. And there's a lot of understanding in the recent years about the approximation with deep neural networks, because we learned about that we can approximate with these networks rather perfect or rather good piecewise polynomials, or basically splines, multivariate splines with 3 knots, and that's great. And then the second point is, because of the network structure, it's easy to approximate also. If you can approximate some kind of function, you can approximate compositions of functions. And that leads to great results about dimension reduction in high-dimensional regression problems. And there are, as I told you already, there are several aspects on the deep learning. One is the approximation. The second one is the generalization, because you learn this function from some noisy data. This is nowadays also well understood. If you use if you use underparameterized neural networks, then you can just use the classical Wapnick-Jovanenki theory. That's well understood. But the big open problem is the optimization. So somehow you define your estimate by minimizing some empirical risk, and then you have to solve this minimization problem. And that's where the overparameterization comes into play, because there was a recent line of research tried to show, okay, who actually showed, if you use overparameterized neural networks, then it's easy to solve the optimization problem, because you will find, even with gradient descent network, which interpolates your training data more or less. But I have strong doubts whether that's successful in terms of generalization. Okay, I think that's my comments.
Thank you very much, Michael. The papers by Michael and the paper by Belkin et al. On PNAS that Michael has referenced are actually on the content page of our library. So I think I did receive quite an amount of questions, which was expected, but we're like 4 minutes to the end of this panel. So I think I'd like to thank Dave and Don and Mike and Michael very much for their contribution and for making time today. Thank you very much. It's been great having you here.